Finally, our Chapter 4 discussion of reactions in aqueous solution is going to focus on the other two types of reactions in aqueous solution that we're going to speak of: acid-base neutralization reactions as well as oxidation reduction reactions, also known as redox reactions. We're going to conclude our discussion with a few words regarding concentration, a means of expressing how much solute there is in a given solution. Acids and bases. In order to understand the nature of an acid-base neutralization, we need to understand what an acid is, and conversely, what is a base. Well, an acid is a substance that when you place it in water is going to dissociate, break apart in order to form H plus ions. Now, if you think about it, H plus, a hydrogen atom that has lost an electron, is simply a proton. A hydrogen atom is made up of a proton and an electron. So if that atom loses an electron, then it is essentially just a proton. So for this reason, acids are often called proton donors. If you place it in water, it will increase the amount of H plus in solution. And here we see a few examples of some common acids: hydrochloric acid, nitric acid, sulfuric acid, and acetic acid. Acetic acid is one of the two components in a bottle of vinegar. The other component is water. Now, there are many other substances that can be referred to as acids. Milk contains lactic acids. Vitamin C is known as ascorbic acid. Tartaric acid is an acid that is found in many fruit, such as grapes. Formic acid is an irritating chemical that's present in the venom of some ant species. And boric acid is an acid that from time to time can be used as ant poison. Go figure. So what really happens when you place that substance into water? Well, acids dissociate into the H plus cation and an anion that is essentially everything that's left in the molecule. So here we see three examples of acid dissociations. HCl, which is hydrogen chloride. When you place it in water, it forms HCl, or hydrochloric acid. That HCl breaks apart into the H plus cation and the chloride anion. Nitric acid, which has the formula of HNO3. When you place hydrogen nitrate in water, it is going to form nitric acid. And that's going to dissociate, break apart into H plus and the nitrate anion. Lastly listed, we see acetic acid, where when we place hydrogen acetate in water, it is going to break apart into H plus and the acetate anion. Now you will notice that the double-sided arrow exists in one of these three equations. Once again, that speaks to the idea of whether or not the dissociation takes place completely or only partially. On this slide, we see that hydrochloric acid and nitric acid are both strong electrolytes in that they completely dissociate, while acetic acid is a weak electrolyte and only partially dissociates. Conversely, bases are substances that when you place them in water, they're going to increase the concentration of the hydroxide anion. So what I have listed here are three examples of strong bases, substances that when you place them in water are literally going to dissociate into a cation and the hydroxide anion. So sodium hydroxide is going to dissociate into Na plus and the hydroxide anion. Potassium hydroxide and lithium hydroxide, their dissociations are shown as well. Now notice that I was very careful in the wording of the definition of a base. I said that a base was a substance that increases the amount of hydroxide when dissolved in water. And that's for a very specific reason. Acids increase the amount of H plus in solution. Bases increase the amount of OH minus in solution, while acids have to have hydrogen in them so that they can break apart into H plus and the corresponding anion. Bases do not necessarily have to have OH minus in them. If you look at the bottom of the slide, you will see the reaction of ammonia with water. Ammonia will remove one of the hydrogens in the form of H plus from water and in turn increase the amount of OH minus in solution. So ammonia is considered to be a base because the products of the reaction of ammonia and water are the hydroxide anion and the ammonium cation. So if we see an increase in the amount of OH minus in solution, then that substance, the substance that has been dissolved, is a base. Now it turns out that ammonia is a weak base, but that's a story for another day. Now, how do we know if an acid or a base is a strong acid or a strong base, a weak acid or a weak base? Well, in the same idea of electrolytes, where the terms strong and weak speak to the extent of dissociation, not necessarily the potency of the substance in question, a strong acid will completely dissociate in water, while weak acids will only partially dissociate. Strong bases completely dissociate in water, producing a metal cation and a hydroxide anion, while weak bases will only partially react with water to produce hydroxide anions. Here we see a list of strong acids and strong bases. Now I want to draw your attention to the list of strong acids. In your textbook, in table 4.2, you're going to see 7 strong acids listed. I am here to tell you that there are not, hear me again, there are not 7 strong acids. There are 6 strong acids: hydrochloric acid, hydrobromic acid, hydroiodic acid, as well as perchloric acid, nitric acid, and sulfuric acid. Now, on your table, you will see underneath where I've marked out the term chloric acid. Chloric acid has the formula of HClO3. And I have eliminated chloric acid from this list for this very reason. Chloric acid does not completely dissociate in water. That's it, point blank, period. While a significant amount of chloric acid will dissociate, it doesn't go completely. And to simply say that something runs 95% of the way and call it complete would be, well, it would be incorrect. So what we see are 6 strong acids: hydrochloric, hydrobromic, hydroiodic. All 3 of those involve hydrogen interacting with one of those halogens. And perchloric, nitric, and sulfuric, all of them involve hydrogen interacting with one of our polyatomic ions. So there are 6 strong acids. You've probably never heard me say the words methylmalonic acid. But if I were to ask you right now, is methylmalonic acid a strong acid or a weak acid? You can immediately say it's a weak acid. Why? Because it's not one of these six. It's not on the list. Acetic acid is a weak acid. It's not on the list. Tartaric acid is not a strong acid. It's weak. Why? It's not on the list. Hydrofluoric acid, HF, is probably one of the most dangerous compounds that I've ever been in a laboratory with. Hydrofluoric acid will dissolve glass. I just want you to think about that for a second. If somebody ever walks up to you with a beaker of hydrofluoric acid, you can immediately say, no, that is not hydrofluoric acid, because if indeed that was a beaker, a glass beaker of hydrofluoric acid, it would have dissolved and there would be mayhem. Right? That being said, hydrofluoric acid will also dissolve bone and flesh and many ceramics, a lot of things. But hydrofluoric acid is considered to be a weak acid because it does not completely dissociate. Once again, strong and weak has nothing to do with the potency, with the it's gonna get you factor. It's simply the extent of dissociation. And here we see a list of strong bases as well. I know that seemed like a bit of a throwaway comment, but there are some strong bases too. At some point in the future, I've got a feeling that I'm going to ask you about those 6 strong acids. So now that we know what an acid is and what a base is, we can talk about an acid-base neutralization reaction, yet another one of the reactions in aqueous solution. Well, when an acid reacts with a base, the result is water and a salt. Now, a salt is simply an ionic compound that will dissolve in water. Commonly, we think of sprinkle, sprinkle on your French fries sodium chloride as being salt, but that is just one type of salt. Right? A salt is simply an ionic compound that will dissolve in water. So if we look at the following equations that speak to the reaction of a strong acid and a strong base, we will see the formation of water, and in this instance, sodium chloride or salt. So the molecular equation shows us reacting HCl with NaOH to give us liquid water and aqueous sodium chloride. If we were to look at the complete ionic equation, what this actually looks like in solution, we know that a strong acid like HCl is going to break apart into H plus and Cl minus. We know that a strong base like sodium hydroxide is going to break apart into Na plus and OH minus. On the other side of the equation, we see the formation of water and sodium chloride. Sodium chloride is soluble in water, so it's going to break apart into Na plus and Cl minus. So this gives us the complete ionic equation. But the net ionic equation, which shows what exactly is taking place in solution, what reaction is actually happening, eliminates those spectator ions. And if you look in the complete ionic equation, you will see that sodium appears on the left-hand side and the right-hand side in the same form. And the chloride anion appears on the left-hand side and the right-hand side in its ionic form. So sodium and chloride are spectator ions, which can be removed from the equation when we establish the net ionic equation. So what happens when you take an acid and you combine it with a base? Well, the H plus from the acid reacts with the OH minus from the base and simply produces water. A neutralization reaction, wherein we see the acidic properties of an acid being neutralized in order to form water, the basic properties of a base being neutralized in order to form water. Some neutralization reactions don't necessarily result in only water and a salt. Now, those two things will be products, but there's some neutralization reactions that also see the formation of a gas. If the base in question is a carbonate or a bicarbonate, bicarbonate has the formula of HCO3 minus. It's one of those polyatomic ions on your list that I didn't ask you to know. But if in fact those two are to react with an acid, we see not only the formation of salt and water, but we also see carbon dioxide being formed. If you look at the first equation, calcium carbonate reacting with hydrochloric acid, in order to produce calcium chloride, carbon dioxide, and water. This type of equation speaks to perhaps something that we might encounter if we have a little, maybe we eat something a little spicy, a little something that kind of kicks up a little acid reflux. Excuse me, pardon me. If you add a base in the form of calcium carbonate, a base which, by the way, is acting counter to an acid, a base which, by the way, is acting anti to an acid, a base which is acting, wait a minute, anti-acid, anti-acid, antacid. Calcium carbonate is an antacid, which means that it is a base. It can neutralize the excess HCl and produce calcium chloride, which is a soluble ionic compound which will be flushed away, water, which will help doing the flushing away, and carbon dioxide in the form of, well, perhaps a belch or a burp. I'm sorry. It is what it is. That's the nature of it. In the second equation, we see sodium bicarbonate reacting with hydrobromic acid in order to similarly form sodium bromide, a soluble ionic compound, carbon dioxide, and water. It appears I may have jumped the gun just a little bit when referring to antacids, but hey, if I can't infuse that information in the lecture, then what good am I? One of the practical applications of acid-base neutralizations involves the neutralization of stomach acid, excess stomach acid, where we see things like Alka-Seltzer, which is sodium bicarbonate, or Tums, Tums. At the bottom of the list, we see Tums in the form of calcium carbonate. And also we see things like milk of magnesia, which is magnesium hydroxide, Mylanta, which is a combination of magnesium hydroxide and aluminum hydroxide. Rolaids, you get the gist. A lot of different compounds whose properties act counter to that of an acid. So we call them antacids, but in short, they're all basic. This brings us to the last of the three types of reactions in aqueous solution that we're going to discuss: oxidation reduction reactions. Now, in order to understand oxidation reduction reactions, we need to understand the two terms oxidation and reduction. Reduction, and I simply refer to reduction first because in short, these are called redox reactions. If you look at redox, it's a combination of a shortening of reduction and oxidation. Reduction is a process by which a substance gains electrons. Oxidation is a process by which a substance loses electrons. So the loss of electrons is oxidation, while the gain of electrons is reduction. And just as a mnemonic, a short little blip to allow you to remember which one is which. If you think of the term oil rig, oxidation is loss, reduction is gain. Now, the two processes cannot take place without one another. They must happen simultaneously. If I am to give away $1 million, there has to be somebody willing to take $1 million. If I simply take $1 million in one of those cartoon money bags with the big dollar sign on it, and I just sit it in the middle of the table, that's still my money until somebody takes it. The two processes must happen concurrently. I can't give unless somebody takes. I can't take unless somebody gives. So electrons can't be lost by one substance unless they are gained by another. And these two processes, as I mentioned, happen simultaneously. So we're looking at an equation here. The reaction of calcium with oxygen in order to form calcium oxide. Now, the image gives rise to a discussion of what undergoes oxidation and what undergoes reduction. But before we understand what this image is suggesting, we need to understand a little bit more about the concept of oxidation, and specifically the concept of oxidation number. In order to determine whether or not an oxidation reduction reaction has occurred, we must monitor the oxidation number of each element in each compound or in each substance. Now, we assign an oxidation number based on a set of rules. Yes, again, based on a set of rules. And those rules are to come on the following slide. But in the same way that we were able to determine whether or not an acid-base neutralization reaction took place, simply by looking at it. If you see an acid and a base as reactants and a salt and water as products, then that is an acid-base neutralization. If you see the formation of an insoluble ionic compound as the result of mixing two soluble ionic compounds in water, then that is a precipitation reaction. And you can quickly look at an equation and determine if it is a precipitation reaction if you see an insoluble ionic compound as a product. But it may not be so easy to, at a first glance, determine if a reaction is an oxidation reduction reaction. So by assigning an oxidation number to each element, we're going to be able to keep track of that oxidation number as we go from product, or rather from reactant to product. If we see a change take place in the oxidation number of a given element, then we will be able to assign this reaction as a redox reaction. Now, it should be noted that this is simply a bookkeeping method. The idea of oxidation number doesn't refer to a charge that an atom has, because atoms don't have charges. Ions have charges. And we're going to talk about the nature of how we assign oxidation numbers in a few seconds. And here we go. For an atom in its elemental form, the oxidation number is always 0. What does that mean? That means if iron or carbon or aluminum or sodium or gold or diatomic hydrogen or diatomic nitrogen, if any of these things appear in an equation as the element itself, the oxidation number of that element is going to be 0. All right. So in the equation that speaks to the combination of carbon and oxygen to form carbon dioxide, carbon would have an oxidation number of 0 in its elemental form. Oxygen would have an oxidation number of 0 in its elemental form. Now, by the time we get to carbon dioxide, those oxidation numbers will change based on rules that we're going to learn in just a moment. Rule number 2 suggests that in binary compounds with metals, that means a binary compound, 2 elements, one of those elements being a metal, the other being one of the subsequent categories that we're about to speak on. A group 17 element is going to have an oxidation number of -1. So things like fluorine, chlorine, bromine, and iodine, when they are in binary compounds with metals, they have an oxidation number of -1. The group 16 elements, things like oxygen and sulfur and selenium and tellurium, they're going to have an oxidation number of -2 in binary compounds with metals. And things like nitrogen and phosphorus and arsenic, group 15 elements, will have an oxidation number of 3, or rather -3, when in binary compounds with metals. Now, I know you may be saying, well, what about when it's not a binary compound with metals? Well, there are other rules to address what these substances' oxidation number would be. Please note the importance of rule number 2, in that the term in binary compounds with metals is in bold. Okay, that's all I want to say about that. In compounds, group 1 elements, those alkali metals, sodium, potassium, cesium, rubidium, francium, have an oxidation number of +1. And group 2 elements, things like calcium and beryllium and magnesium and strontium and barium, they're going to have an oxidation number of +2 in compounds. In compounds, the oxidation number of fluorine is -1. That's it. If you see fluorine combined with something else, its oxidation number is going to be -1. It doesn't matter if it's a metal, if it's a non-metal. The oxidation number of fluorine in a compound is -1. In most compounds, the oxidation number of hydrogen is going to be +1. Now, there are exceptions to the rule. These exceptions are a specific class of compounds known as metal hydrides, where hydrogen is bonded to a metal, so that we see the oxidation number of hydrogen being -1. I'm not likely to give you any examples on a quiz or a test of a metal hydride. So operate with the understanding that the oxidation number of hydrogen is typically going to be +1. In most compounds, the oxidation number of oxygen is -2. Once again, there's an exception to the rule, a class of compounds known as peroxides, where the oxidation number of oxygen is -1. And I will not speak to peroxides, so operate with the understanding that in most compounds, the oxidation number of oxygen is -2. Now, there are a lot of elements that haven't been addressed yet, and they're not going to be addressed directly. But these last two rules kind of encompass all substances. It says for atoms in an ion, the sum of the oxidation numbers is equal to the charge on the ion. And that's whether it's a monatomic ion or a polyatomic ion. And we'll talk more about that in just a moment. And for atoms in a neutral species, it means a compound wherein we see no charge. A formula unit if it's an ionic compound, a molecule if it is a covalent compound. The sum of the oxidation numbers is 0, because once again, a neutral species does not carry a charge. So let's refer to the oxidation number in a polyatomic ion. The oxidation number, which from here on I'm going to refer to as ON, a stylized, italicized ON, it can be deduced. So let's take a look at nitrogen. There's no rule specifically speaking to nitrogen. All right. So if we have nitrogen in the ammonium cation, which has a formula of NH4+, the rule from the previous slide suggests that the sum of all of the oxidation numbers of all of the elements is going to equal the charge. And since the charge on this ion is +1, then when we add the oxidation number of nitrogen to the oxidation number of 4 hydrogens, then that's going to have to equal positive 1. So the oxidation number of nitrogen plus the oxidation number of hydrogen and hydrogen and hydrogen and hydrogen is going to equal a positive 1. Well, if each of those oxidation numbers of hydrogen is positive 1, then that means that when we add those together, subtract 4 from both sides, then we find the oxidation number of nitrogen that remains is a negative 3. The oxidation number of a monatomic ion is simply the same as the charge that that ion carries. So in the case of the iron plus 3 cation, the oxidation number would be plus 3. For the oxide anion, it would be minus 2, and for the fluoride anion, it would be minus 1. The oxidation number of an element in a compound can similarly be deduced in the same way that we saw for a polyatomic ion. So if we're looking at the sulfur in sulfur dioxide, we don't know the oxidation number for sulfur because there's no rule regarding sulfur. But there is a rule regarding oxygen. And there is a rule suggesting that the sum of everything must be 0 because sulfur dioxide is a molecule, a neutral compound. So if the oxidation number of oxygen is minus 2, then by summing up all of the oxidation numbers to equal 0, we see the oxidation number of sulfur must be a plus 4. So how do we determine whether or not an oxidation reduction reaction has taken place? Well, you evaluate the oxidation number of an element before the reaction as a reactant and after the reaction as a product. And if a substance has undergone a change in oxidation number, then you best believe that oxidation and reduction have taken place. So let's look at the original equation that speaks to the reaction of calcium with oxygen in order to form calcium oxide. Well, before, each element is in its elemental state. So the oxidation number of calcium in calcium is 0. The oxidation number of oxygen in oxygen is 0. But after the reaction, we see calcium oxide. Calcium oxide is a binary compound where we see a metal and a nonmetal. Since oxygen is a group 16 element, oxygen in a binary compound with a metal is going to carry an oxidation number of minus 2. And just in case you weren't aware, there is a rule regarding oxygen where oxygen in most compounds is going to be minus 2 anyway. Calcium, well, in compounds, calcium is going to be plus 2 because it is one of those alkaline earth metals. But also, we know that the sum of all of the oxidation numbers in a molecule or in a compound is going to be 0. So if oxygen is minus 2 and there's one calcium there, then calcium has to be a positive 2. So as a result of this reaction, we see that calcium goes from an oxidation number of 0 to a positive 2. Calcium is becoming more positive. Oxygen is undergoing a change in oxidation number from 0 to minus 2. Oxygen is becoming more negative. Well, if a reaction involves the exchange of electrons, and electrons are negative, if something becomes more negative, that means that it has taken on electrons. It has more electrons after the process than before. If something becomes more positive or less negative, that's because it has lost electrons. So over the course of this reaction, we see that calcium has lost electrons in going from a 0 to a positive 2. Since oxidation is the loss of electrons calcium has undergone oxidation. Another way of saying that is that calcium is being oxidized. Right? Oxygen, on the other hand, has gained those electrons. And since reduction is the gain of electrons, oxygen has undergone reduction. In this reaction, oxygen is being reduced. Now, the last sentence associated with each of these elements is important. It's underlined, and it suggests the job that that element is performing. If oxygen gains electrons, it is because calcium lost them. So the reduction process that happens to oxygen only happens because calcium gives up its electrons. So calcium causes oxygen to be reduced. Therefore, calcium is considered the reducing agent. It causes reduction to take place. Oxygen, on the other hand, is the landing spot for those electrons. Calcium can't lose electrons unless they have somewhere to go. So oxygen has facilitated the process by which calcium loses electrons. Could calcium undergo oxidation without something to take those electrons? No. So oxygen, in taking those electrons, makes the oxidation process take place. Oxygen is therefore the oxidizing agent. Now, in order to keep up quantitatively with the amount of solute in a given solution, we tend to refer to the concentration of a solution. The term concentration refers to the amount of solute dissolved in a given amount of solution. And one way of expressing concentration is through what we call molarity. Molarity. The molarity of a solution refers to the number of moles of solute, not grams, but the number of moles of solute in a given number of liters of solution. I'm going to repeat that. And I'm also going to repeat where things can go wrong. So let's not let them go wrong. Molarity is the number of moles of solute, not grams of solute, but moles of solute per liter of solution, not per liter of solvent, but per liter of total solution. Now, molarity can also be used as a conversion factor when converting back and forth between moles and liters. In other words, if you see three things in an equation and you know two of them, you can solve for the third. If I have a solution that is described by a particular molarity, and I know how many liters of solution I have, I can determine how many moles of solute are in that amount of solution. Here's an example of a calculation of molarity. If I were to take 1.42 moles of potassium hydroxide, and I were to place it in enough water to make 2 liters of solution, that solution would have a specific concentration. There would be a certain amount of solute per liter of solution. So using those values and our equation for molarity, we would determine that we have a solution that would be described as 0.70, or rather, excuse me, 0.710 moles of solute per liter of solution, or 0.710 molar in concentration. So the term molarity refers to the number of moles per liter of solute in a given solution. Now, I don't know of any balance in the world, any scale in the world that weighs things out in moles. Instead, they weigh things out in grams. So if you are instead given the mass of a solute, for example, if I were to say 39.2 grams of sodium hydroxide in enough water to make 3 liters of solution, then you would have to convert that mass in grams to moles using the molar mass of sodium hydroxide before you could do the molarity calculation. Now, how do we create a solution of a given molarity? Well, we weigh out a known mass in grams, and if you know the nature, the identity of the solute, then you can convert grams to moles using the molar mass. So you know how many moles of solute you've weighed out. You then add it to a volumetric flask, a flask that has very specific delineations with regards to volume. And you add enough solvent to achieve a total amount of solution. Now, I don't say simply add solute to solvent and determine the molarity based on those numbers. Because if you take 1 liter of water and you place 5 grams of sodium chloride in 1 liter of water, since volume is the amount of space that something takes up, it could take up more space than simply 1 liter by adding more stuff to it. So that's why we don't refer to molarity in terms of moles per liter of solvent. It's moles per liter of total solution. Now, once a solution is made, a solution can be diluted, or we can see the concentration reduced. The term dilute simply refers to less concentrated or of a lower concentration. And the way that a solution can be diluted is by adding solvent. All right. In the mathematical equation, that is molarity equals moles per liter. If you increase the number of liters of total solution while keeping the number of moles of solute the same, then you will see a reduction in the molarity, an expression of concentration. This final slide speaks to the simplicity or the complexity of applying stoichiometry to solution chemistry. Well, we know that reactions take place in molar amounts. 1 mole of this substance will react with 2 moles of this substance in order to give 1 mole of product, for example. Well, in a solution, if we have a molarity, if we have a concentration, then we can determine how many moles of solute are in a given amount of solution. If we have a 0.105 molar solution of sodium chloride, that means that we've got 0.105 moles of salt per liter of solution. So in that solution, we have 0.105 moles of solute. If we were to mix the entirety of that with another reactant in the proper molar amounts, then we could see a reaction take place, which means that everything would go to completion. But you have to figure out the number of moles of solute in each solution and in each sample of solution in order to determine if a reaction mixture involves equimolar amounts or whether one reactant is going to be in excess while one remains the limiting reactant. Thank you for listening. Thank you for reading. And this concludes our discussion of Chapter 4. Thank you, and stay safe.